So we're going to start by proving the associativity of and. Now, with pattern matching, this is actually pretty easy because we can just use the same thing that we used last time to pattern match with our intro. And we're going to be using the angle brackets. Type those backslash less than. And we're going to get the P and Q from the hypothesis here. We're going to call that P and Q. But then we're going to recognize that we can use another pattern match again to match that inner pattern. And that'll look like this, and then R. So now we've matched our first pattern here. And here's where I realized that what we're actually proving here is not an if, it's an if with two Fs. This is an if and only if. That means that tactic intro n is failing because it's saying I can't assume the hypothesis if we're not using an implication, right? So if I were to change this to an implication, Lean would be okay with that. But we actually have to prove both directions. So I'm not going to use the way the book does it. The book likes to use constructors like or.alim, or I think there was a constructor for and somewhere here. Anyways, yeah, something like this to show implication. We're going to do a bit more one step at a time. So we're going to show using another really important tactic, which is just to show that you have a part of your proof. That tactic is going to be called have. And that's just to show a lemma, basically. It's almost the same thing as lemma, but you're just inside the proof scope. And we're going to have, we're going to call it MP for modus ponens because we're going to go from left to right here, and it's going to be of type. And it's just going to be the same type, but with implication, right? I am. And we're going to prove that by, now we get to use our intro. And of course we can use exact here, question mark, because I'm too lazy to type. Unfortunately, exact with a question mark doesn't work. Even though it should be pretty clear how we can finish this. We just put P in the first and Q in the second one. And that works for the first one, for the first goal. Okay, so it's just reordering parentheses, right? I'm just going to copy this lemma, paste it over here, and we'll just reorder stuff, right? So P and Q goes on the left this time. And then we have this up here instead, right? So our intro and exact. And now we're done. Actually, we're almost done. We have to actually combine these two things into our if and only if statement. And we can do that by saying MP, NPR in angle brackets. Another way to do that would be to use the actual constructor name, if.intro np_npr. Okay, so that was pretty easy. We didn't really get stuck there. In the next example, we're going to get stuck. This one is this example from the book that they show. They actually give a solution for. Where did they give the solution? Down here, I think. Yeah. So they give a solution with if.intro, they give lambdas and stuff. And for a beginner, especially a beginner who's not familiar with functional programming, this kind of structuring of a proof is difficult to understand. And I'm realizing now that I forgot to do this in the functional style, but the functional style would look very similar because you can do pattern matching in the argument for a function. So real quick, that would just look like this. I'll just prove one direction so it doesn't take too much time. we're going to have example P and Q and R implies that, and we're going to do lambda, and then we're going to immediately pattern match with the angle brackets to get P, Q, and R. Okay, and this is going to return, put on another line, we're going to return exact this. Great. Oh, there we go. Okay, so that's just a lot shorter and more concise, but also probably a bit harder to read for a beginner. Okay, so let's get into P and Q or R. If and only if P and Q or P and R. So this is distributivity over or, right? We're distributing the P and into each term inside the or, and vice versa. So I'm going to use the same format again by splitting the problem into parts with have. Right? So we're going to prove the first way first, the modus ponens first, and then we're going to prove modus ponens in reverse. So I'm going to start by filling out my haves with sorries. This is an important proof strategy. You don't want to rush into proving your lemmas before you can show that they're actually useful to prove your goal. And so I'm going to go ahead and do that here. P and, let me just finish this, Q or R. And we're going to assume that if we have shown both of these, NPR and MP, we're going to make sure that if we've shown both of these, that we can actually prove the end goal. Okay, good. So we can. So now all we have to do is fill out each sorry. And so we know that if this is an and, we can do pattern matching. So we're going to do our intro, and we're going to do P, Q, or R here. But remember that we had a way to do pattern matching for ors as well, right? And there's no rule saying we can't do both. In the other file in episode 1, we looked at pattern matching on an or with, in parentheses, a bar pattern match that matches a sum type. So this is a product type because you have both P and Q or R. Q or R is a sum type because you have Q or R. So that's going to be with parentheses, Q or R. Okay, so now we have everything, and you can see that doing that split our goal into two cases again, which makes sense because if you're going to pattern match on Q or R, you have to show two cases where either one is true, and you don't get to assume the other one. So in our first case, we always have P in both cases, but in our first case we have Q, and in our second case we have R. All right, so now we have to show each case, and again I'm going to do best practices here for proofs. We're going to fill out the proof with sorries for both cases, and we're going to work on one at a time. So now we have to show P and Q or R, P and Q or P and R. And we have almost everything to do that. We don't have an R, so we can't really build this side, but we can definitely build this side, the P and Q. So let's just go ahead and do that. So we're going to have, we're going to say we have P and Q, and we're going to have it by just exactly the constructor P, Q, because both of those variables are in scope. We're going to have to say exact, right? Uh-oh, what's happening here? Invalid constructor. Constructor must be an inductive type. Okay, hold on a second here. Do I have to give a type, maybe? P and Q. Okay. So Lean didn't know how to infer the constructor here. I wouldn't have had to do that had I been explicit and said and.intro for the and constructor. I wouldn't have had to give a type name. And now we're getting the red squiggly because, well, we haven't finished our subproof. So now that we know P and Q, we know from logic that if you know P, then you know P or Q. But suppose you forgot how to do that in Lean. Let's just use exact, right? And exact is going to tell us, hey, you forgot it's or.inr for injective right. Great. And I don't like or.sim, so we'll just switch it to the left because that's equivalent. Okay, what about the other one? Well, the other one, we know R, and we have to show P and Q or P and R. And this will work very much, this is going to be symmetrical, right? So P and R instead of P and Q. We're going to and.intro P and R, and we're going to do probably another exact or.inr. Great. And so now we're done with the first way. Now we just have to show the second way, right? For the second way, it's a bit different. We're given at the top level of this expression tree. Trees are expressions. In this case, since all the operators are binary, this is a binary tree. The top level node is going to be this or, right? And you know that because when you hover over, and this is where using Visual Studio Code is important, and unfortunately to my inner programmer, it makes my inner programmer sad that this is the case, but it is quite fun to have this interactive window because you can mouse over something like the or here, and Visual Studio Code is helpfully, Lean4 is helpfully showing you that when you do that, the expression that's highlighted is the full expression of that or, right? So in other words, this or contains this whole tree. That's the root node of this whole tree is this operator. Whereas if you mouse over the and, you can see that, well, it's making clear the implied parentheses around the P and R or the P and Q. And so if you ever forget, or have trouble understanding where the parentheses are, this is very helpful. So the P and Q here and the P and R are children of an or. And in an or, this is a good time to introduce the cheat sheet. So there's actually a Lean4 cheat sheet. Basically, when you have an or and it appears in the hypothesis, you're going to want to use the cases, right? So if you ever forget, like, okay, what pattern matching am I supposed to use? You can use this cheat sheet, and it's quite helpful. Now, these are for tactics, not for functional programming. So just keep that in mind. Like, for example, implies. Fundamentally in Lean, the only way to prove an implies is with a lambda expression, but tactics can do that for you. You don't need to do that. So now we know how to pattern match that. But we've been using our intro just fine. So let's just use the same thing, right? In our intro, and now we're going to have parentheses on the outside and braces on the, or not braces, angle brackets on the inside, right? Because now instead of an and as a root node, we have an or as a root node. Okay, so then we have Q, but again, we know how to pattern match an and, P, and then we're going to have a bar, and we're going to have P and R. Great. So this is doing a lot of work at once, and I'll show you in our term mode solution. Let's just make a term mode solution like here. I'll show you how to do this a little bit more explicitly instead of having all this magic happen in our intro. Okay, so now, of course, if we had one bar up here to split the goal to two cases, we have to handle those two cases. We'll do that with sorry. And now let's make sure we put our cursor in the correct place, and we get, we have to show P and Q or R. Well, how do we do that? We need to show something, right? So let's use exact to figure out that something. And because we're in term mode here, remember we already used exact, right? We're in term mode. We have to use a variant of this for term mode, which is the actual function, exact %. And now this is what we need to use when we're inside, when we need an expression, right? And now we can just do or.inrq. Great. Set that to the left. Okay. And then I don't think exact can do two steps at once here. No, it can't. So let's do the opposite. And we know it's going to be or.inr. Oh, no, it's still going to be inl. But this time instead of q, it's going to be r. And it's going to be on the right side again. Okay, what is this from? We are getting a type mismatch that R is type R, but is expected to have type P. Okay, am I forgetting exactly what we're supposed to prove here? No, we're supposed to prove P and Q or R. So this just means that we've forgotten to change, INL to INR. Okay, now we're done with that. And now all that's left to show is to quickly go through this in term mode so that you understand how to build up these, what are basically functions. Underneath the hood, these tactics are building up functions, building up lambdas, right? So to do that, we're going to do, we don't get to use by here, we're going to do if.intro. If.intro is going to take two arguments, both of which are functions. P implies Q and Q implies P. Because they're functions, we're going to be able to say lambda, and then we need to say P and Q or R. So I'm going to do half the pattern matching for demonstration purposes in the hypothesis and half of it in the function expression to demonstrate how to do pattern matching inside a function. And that will be with match P or Q with, and then it's just our two constructors, right? Or.inl and or.inr. And in this case, we have HP and HQ, right? Oh, HQ or R. Okay. And now I'm being a little inconsistent here. Just remember that when I'm using P and Q down here, it's actually a value of type P. It's actually the hypothesis of type P. And a bit better practice would be to call it HP, because it's a little confusing to have a value have a type of the same name. It would have been better if we had used, if just the book had used uppercase letters for the propositions, because they're supposed to correspond to types anyways. So, well, that's not convention. Okay, how do we do this? Well, the first one should be super easy, right? I think we can get away with exact. We can. Uh-oh. So now and or left.mp, this is a theorem that's proving our theorem. So that's a bit unfair to use here. No, we don't want to do that. We want to say, we need to prove that P and Q or P and R, right? In the first case, again, right? So this is going to look, this should look very much like in the first case of the proof. But I'm not actually going to waste time doing this whole thing again. I just wanted to show you the match the equivalent of match when you don't get to like case split. You know, you don't want to use the tactic feature of having different cases, and you want an expression that pattern matches on them, right? Okay, and how do I pattern match on an or in the second expression? Well, we should be able to do P and Q or P and R, right? Unfortunately, this syntax does not work. Our intro, the R intro tactic can use this syntax, but it's not available to us in function mode. In term mode, as far as I know, I could definitely be wrong about that. But we still have the usual match expression, right? And we can, of course, say, you know, H or for some name for the hypothesis, and then match H or with, and then, of course, both cases. Okay. Oops. And let's just rename these to underscore, so I don't care about them. But these are the two ands, right? P and Q, P and R. Okay, but if I wanted to do pattern matching on an and instead of an or, what does that look like, right? And so that would look like this. If we comment this out, and remember that we're taking, you know what, I'm just going to replace it. We're taking an and here and pattern matching on its two sides. But what if we wanted to use a match statement for both of those, right? So we'll just take in our hypothesis and the whole thing and match on the whole thing. And that would look like this, where we give an and.intro and the two arguments to that constructor. So we have and.intro HP, and then and.intro some or pattern over here, which I'm not going to bother with. I'm just going to call it underscore. Just make sure this is the right type. Yeah, okay. And we'll have something similar down here. So we would have and.intro HP, whatever. Okay. But this is a redundant alternative, right? And that's because really what I'm trying to get at here is that and only has one case. Obviously in this expression, because and has a nested or, it has multiple cases if you pattern match on the or nested. If you don't pattern match on the or, like I'm doing here, then this case is redundant, right? And so basically I'm just trying to illustrate an example of this. P and Q, let's do a simple one up here. Super simple commutativity, P and let's do Q and P. Okay. Super simple lambda H and goes to match H and with, and there's one pattern. And that pattern is the single constructor for and, EQ, and we're going to return an and intro UP. Okay. And this is just to illustrate that pattern matching is for all inductive types, not just for or. So or is a sum type, but you can use pattern matching just fine on product types like and. It's just that you get one constructor, but with all of the data kind of as arguments. So and has one constructor with two arguments, or has two constructors with one argument, right? And so That makes sense because I mean the product types are they have all of their data, and then some types have at the top level an kind of like an option or in lower level programming you would call this an integer that tells you what kind they are, right, at the top level, and then inside each one you have less data, right, compared to an AND.